Okay. In the previous session, we looked at the locking in type 1 PLL, and we found the stable solutions while defining the phi error dot by k. So, let me just recall what we have looked at quickly. So, this was our PLL, type 1 PLL with R and C and VCO connected in feedback. This is V in and V out. What we have observed is we tried to find the solution in the lock case where we were looking at this delta omega 0 by k minus sign of phase error. If this equation has a solution, then the PLL locks, otherwise the PLL does not lock. Okay. Now, the question arises, the PLL does not lock. So, what does it do? Okay. You give the input signals, you have initial frequency error. So, at time t equal to 0, my omega in is equal to omega, my omega out is omega free, right. Vc was equal to, Vc is equal to 0 here. Okay. So, you have phase error dot which is given at the top, you have frequency error at the beginning. So, delta omega 0 is nothing but omega minus omega free. If this frequency error is large, the PLL does not lock. Question is, what does it do? Okay. So, let us figure out what does it do. So, I will plot the same thing for the case when you do not have a solution for this equation. So, let us see this. You have here as phase error, and this one is phase error dot by k, and assuming that there is no solution, I will plot okay. So, this is the kind of waveform you have. You do not see the blue curve crossing. Blue curve is nothing but the what you see the right hand side of the above equation. You do not see this crossing the x axis at all. Okay, and this is nothing but delta omega 0 by k here. Okay, well, it does not cross, that is fair enough, no problem with that. What does it do? That is, to figure out that, let us note these points. So, this is minus pi, this is plus pi. Okay. So, if I connect everything in the PLL as shown to you here, you will have error voltage and control voltage, just that these voltages will not settle to a fixed value because it does not lock. So, what is happening here is the following. If you look at on this top the upper part of this curve, which is here, right, and similarly the lower part which is here. In both these cases, what you see here is, I will just write this, but you pick up this particular point which is minus pi by 2. At phase error equal to minus pi by 2, what you see is phase error dot by k is equal to, you can work this out, this is nothing but delta omega 0 by k plus 1, or the other way you can say, I will just remove the k from here and say that the rate of change of phase error with respect to time is delta omega 0 plus k. Okay. Similarly, at phase error equal to pi by 2, you will have the rate of change of phase error as delta omega 0 minus k. To be it should be noted here that k is a positive value. Now, when you start this PLL with initial frequency error delta omega 0, and you do not have any solution which gives you that the rate of change of phase error is equal to 0, then the waveforms will keep on changing, or the voltage signals here will keep on changing, and it will not settle to any fixed value. At that particular time, what you observe is from our previous analysis that at some particular phase error, or we have chosen only 2 points, at these phase errors, at one particular phase error, the rate of change of phase error is maximum, and in other case the rate of change of phase error is minimum. Okay. Delta omega 0 by k tells us the rate of change of phase error is maximum, whereas in the other case it tells us rate of change of phase error is minimum. So, the PLL is still running, it is not locked. The only thing is sometimes the phase error changes slowly and sometimes the phase error changes fast. Okay, how does it matter? Let us see that. So, we will try to understand that what happens here. So, for that what I will first do is I will show you the case. Let us pick up simplify it a little bit and consider our mixer standalone or the phase error detector standalone, which is this block, right, phase error detector. In case this is only you are considering only the mixer part. Okay. So, I have V in, I have V out. Okay. And this is, let us say this is not connected in the loop, just to understand the how the phase error would have changed if there was a frequency error, but it was not in the feedback loop. If that would have been the case, the phase error would increase linearly. There is no doubt, right, because if you have frequency error between these two, phase error is nothing but delta omega 0 times t, it is a linear one. Fine. If it is linear, so what I am plotting here is phase error with respect to time. The blue one is for open loop. So, it may start from minus 2 pi, goes to minus pi, then 0, then plus pi, plus 2 pi, and it is going to get all these values at fixed intervals of time, and these fixed intervals of time is nothing but they depend on delta omega 0. So, you are going to accumulate this phase error in time 2 pi by delta omega. Okay. So, this time if I want to write it with respect to this is 2 pi by delta omega 0 if you start from time instant 0. Okay. Starting from minus 2 pi or that is just a reference which I chose, you can choose anything. The important part here is for a mixer in open loop, the phase error will keep on increasing linearly. Okay. Now, we have just analyzed if the frequency error is larger than k, then sometimes the phase error increases slowly and sometimes the phase error increases in a fast manner. Okay. So, both the things will happen. We have seen this, okay, that your rate of change of phase error when your phase error is minus pi by 2 is fast, and then when your phase error is plus pi by 2 it is slow, and this rate of change accumulation of the phase error is periodic in nature. Whatever is happening in one period, the same thing is going to happen in the other period. Okay. So, if we look at the phase error in the closed loop or in the loop where we are having our V out is affecting the mixer input. So, what we will see is that the phase error may start from some value and then it increases slowly and then it may lead to 0 here. Every 2 pi it is going to repeat this. It is not going to increase linearly. Okay. While plotting this red curve, the thing which I have assumed that control voltage is V error. So, in this red plot my assumption is V control is V error and V error is half of sine of phase error, or you can say KPD times sine of phase error. This I have assumed, and only when I assume this, the output frequency will change, and based on the output frequency we have already derived this equation. The thing which we are not proving, writing the exact expression, we are just using these two and saying, because sometimes the phase error increases slowly and other times it increases fast, the change in the phase error which you will see will not be linear with respect to time from minus 2 pi to 0, but it will be non-linear. Okay. So, in this particular case what you see is it accumulates phase from minus 2 pi to pi in larger time. If I call this as delta T1 is larger than delta T2. Okay. This is what we are talking about, right. So, if such is the phase error accumulation, then in response to this phase error, what is our error voltage? Error voltage is sine times the phase error. Okay. If error voltage is sine times the phase error, then what you are going to see is what is the error voltage for the case when your phase error is not changing linearly, and it is always it always keeps on going from minus 2 pi to 0 and 0 to 2 pi, right. It keeps on increasing, but with a different rate of change. So, for this particular case, you understand that the voltage error is nothing but half times the sine of phase error. We are rejecting the high frequency component, which is like omega plus omega in plus omega out. That is something which we have been neglecting so far. So, let us neglect that and only focus on this V error. When the phase error goes from minus 2 pi to 2 pi, that time sine is actually going to be. So, you look at this, your phase error goes from minus 2 pi to 2 pi. So, if I just plot sine waveform, we all know the sine waveform is nothing but this, right. This is your sine waveform. Okay. This is your minus pi and this is plus pi, and minus 2 pi is this and minus pi the other way. Okay. So, when you go from minus 2 pi to minus pi, your half of sine of phase error is positive. It is changing not like a sine wave, but maybe some other waveform, and then during the other half, during the other delta T2 time, you may have, and it returns to negative, right. The same waveform, this waveform will keep on repeating because the PLL never settles. Okay. So, this is going to repeat. Assume that the two waveform which I drew they are the same. This is what you will see as a error voltage, right. Now, this is, and this keeps on happening. Okay. This particular part will keep on always happening. If such is the case, right, which you see here when PLL does not lock, this is the same thing which I did not tell previously, but I showed to you that the waveform just keeps on doing something like this. Okay. And you know that this V error is passed as V control voltage, and when it is passed as V control voltage, even the V control voltage will do the same thing, and PLL is never going to lock. Okay. One interesting part which you can see is the waveform which you are looking here, V error voltage. The waveform does not have a 0 average voltage. Okay. In case the PLL was in open loop, then the V error voltage would be just a sinusoid. In case you have a open loop, your phase error will be something like this, right. It is not equal where like on the plot you do not see it, this has a 0 average, but actually it does. This is like a sine wave, okay, and it is repeated. So, the difference is in open loop, average of V error is equal to 0 for given phase error, for any given frequency error. In closed loop, average value of V error is not equal to 0 even when delta omega 0 is non-zero. Okay, delta omega 0 by k is greater than 1 in our case. That is what I am showing you here. This is what we see here. So, if that is the case, right, there is some kind of information in the V error voltage about frequency error, but it will not be able to lock at all. Okay. The DC value, the average value of this V error voltage which you see here in black is called as whatever that value is Vp, is called as pull-in voltage. Okay. There is a meaning attached to it which we will see later. Okay. So, this is the pull-in voltage. Now, this waveform, the waveform which you see here, right, this waveform is asymmetric in nature. This particular waveform is asymmetric in nature and often referred as asymmetric beat note. Okay, it is like a beat here, it is asymmetric in nature, it has non-zero DC voltage, that non-zero DC voltage is called as pull-in voltage. Yeah, so what can we do with this pull-in voltage? That is something which we need to see. Thank you.